Section 5.5, Factoring Perfect Square Trinomials. Consider taking a binomial squared. This binomial squared means x plus 3 times the quantity x plus 3. And if we use the FOIL method, first terms multiplied together, we get an x squared. If you multiply the outside, we get a 3x. The inside terms multiplied together is another 3x, which 3x plus 3x gives us 6x. Essentially, we have doubled that 3x. And our last terms multiplied give us 3 times 3, or 9. This is the result of taking a binomial square, and it's recognized as a perfect square trinomial, where we just went from multiplying together. If we're presented with this polynomial and we're to factor it, and we want to break it down to what two things, in this case, multiply together to equal it, we can do a quick check. Two terms must be squares. And if we look at the first term, what times what gives us x squared? Well, that's x. The 9 is a perfect square. It results in 3 times 3. And the remaining term must be 2 times the product of those square roots, which it is. It could be the opposite, and if you remember when we factored trinomials in previous sections, if the sign is plus on our third term here, it means both factors have the same sign, and they are whatever the sign is in front of the linear term. So when we want to factor a perfect square trinomial, if it's of the form a square plus double the square root of the first, the square root of the last term, plus the second square, it will factor into square root of the first term. Because this is a plus, both signs are the same, they're both plus, square root of the last term, the quantity to the second power is the factor of that. For a perfect square trinomial of this form, looks exactly like the one above, with the exception of both signs are the same on our last term. They are both negative this time. So we have a square on our first term, the square root is x. We have a square on our last term, square root would be y, and the sign between those two is a negative. So this perfect square trinomial factors into x minus y, the quantity squared. Let's take a look at using that shortcut to help us factor these trinomials here. So looking at this, it helps if you're familiar with some squares. And looking at 81, if you recall, that's the result of 9 times 9. X squared, no question, the square root of x squared is x. To know whether this is a perfect square trinomial, it must pass the test of doubling the product of the square root of the first and the last term. Well, 2 times 9 times x is 18x, so this is a perfect square trinomial. Both signs are the same. Both are positive, so this will factor into an x plus 9, the quantity squared. Now, we could have used the technique of what numbers multiply to give us 81 and add up to give us 18, and we would have eventually gotten to a 9 and 9 that do add up to be 18. But just as a faster way of factoring, a lot of people recognize squares, and let's try that technique here. When our leading coefficient is something other than 1, then we either have to use our guess or check or factor by grouping, which can be quite involved. So a quick check to see if this is a perfect square trinomial is going to save a lot of time in the long run. Looking at the first term, perfect square. 2x times 2x is 4x squared. What about 49? Square root of 49 is 7. The true test is if you take the square root of the first term times the square root of the last term and double it, and it equals the middle term, there you have proof that this is a perfect square trinomial. Well, 2 times 2 is 4 times 7 is the 28. Both signs have to be the same, and what they will be is determined by the coefficient of your linear term. So the square root of the first term was 2x, square root of the second term was 7. Both binomials have a minus, and when we write it to the second power, the square of this binomial results in that trinomial. In the next one, does it factor into a square of binomials? In other words, is this a perfect square trinomial? The square root of the first term is a perfect square for x. Likewise, a 9y times 9y is 81y squared. To check, we'll take the product of the square root of each of the first and last terms and doubling it. 9 times 4 is 36, times 2 is 72 with our xy. Both signs are going to be positive, and so this is a perfect square trinomial. And our first term is a 4x, our second term is a 9y, and it is the binomial square. In this next example, don't recognize 3 or 48 as a perfect square, and they aren't, as a matter of fact. 3 is a prime number with the only factors of itself and 1, which leads us to perhaps a common factor that we should be looking at initially. The greatest common factor is 3, so every term will be divided by 3 to factor it out. 3r squared divided by 3 is r squared. 24 divided by 3 with the same sign is an 8r. And 48 divided by 3 leaves us with a 16. Anytime you have a power higher than 1, you should be suspicious that you can factor this further. And looking at this, the first term is a perfect square, square root is r. The last term is a perfect square, 4 times 4 is 16. The test for this to be a perfect square trinomial is take the product of those square roots and double it. And when we double 4r, we get an 8r. So the trinomial here is a perfect square trinomial, which means it will factor into r. Both signs are the same, both are minus. So an r minus 4 quantity squared. This binomial squared is taking the place of the trinomial. When we factor out a greatest common factor, it always should be included, so that at any time when you multiply this back together, it equals what you have.